Okay, the next topic is thematically a bit disconnected from what I discussed right now. It is the existence of local inertial frames, or some people call it geodesic coordinates. So I will start with the proposal that how about switching to a frame in which the metric components are Minkowski metric at a point, okay, at a point with coordinate x0. So we are in some arbitrary point x0, and I know the metric depends on the reference frame. How about at this point I go from one coordinate system to another coordinate system in which the metric at this point becomes Minkowski, okay, Minkowski metric. So that question can be easily answered, right? We know the transformation law for the metric, general coordinate transformation law for the metric components. So here is the unprimed frame, and here is the elements of the inverse Jacobian, and this is the resultant metric in the new frame. And I want this resultant new metric to be equal to NPTEL-NOC. And this seems like it is not a big deal because if I can manage to doctor the inverse Jacobian components, if I can design them such that this equation is satisfied, I'm done. Okay. So I need to find a general coordinate transformation which will satisfy this equation. So a general coordinate transformation around this point x0. Let's perform this. So I want to go to a frame in which this point x0 will be labeled by the origin. Okay, become the origin. So x prime 0 is origin. And then I'm going to do a Taylor expansion around that point. So x prime of x is an analytic function. So I can always write x prime as a convergent Taylor expansion around x0, right? So this is a convergent Taylor expansion around x0. x0 is in the old coordinate system, and x prime is the new coordinate system. So in particular, at the point x0 itself, all these terms are 0, and you're at the origin. And as you go away from the origin, these corrections kick in. And the idea is that I can set these components, right, such that this becomes the head of the loop. It seems that can be done, and we will work out these components slowly. These Taylor expansions. Our aim is to work out these components, the Taylor expansion components, which are constants. Okay, I'm looking at a manifold which has d dimensions. Okay, big D, number of space-time dimensions. Now this equation is not a single equation because all the metric components are there, and the number of independent components of the metric, since it's a symmetric tensor in d dimensions, is d times d plus 1 over 2. So we need to satisfy this many equations. And the number of parameters we can play with to do this are the first order derivative of the slopes. And how many are there? Well, x prime mu, there are d different components, and nu can take d different values as well. So the number of parameters slope parameters we can play around with is d squared, which is definitely larger than the conditions we need to satisfy, which is d times d plus 1 over 2. So multiple solutions are possible. This is going to be realized in many different ways. How many different ways? Well, d squared is the total number of ways we can do it, minus the total number of constraints we can satisfy, d plus 1 over 2. And this difference is equal to d times d minus 1 over 2. So these are so many independent ways you can change the slope variables such that you go to a frame in which the point x0, at the point x0, the metric appears flat. Okay, and these different ways of accomplishing them actually represent different Lorentz transformations, because once you attain the Minkowski metric, at that point you can also do a Lorentz transformation and you still have the Minkowski metric. So there are many Lorentz invariant ways, or you can Lorentz different ways with which differ from each other in terms by a Lorentz transformation, which will keep the metric Minkowski. All right. So it seems like we can do that at that point, at the point x0. we can change the metric to Minkowski. Now the second question is, well, I'm happy that at that point x0, the metric has been turned into Minkowski, but can I have that in some finite region of the manifold? Okay, finite region of space-time. Can in this finite region, at all points, the metric be converted into eta mu, Minkowski metric. Okay, in a finite neighborhood, not just at the point P, but in a finite neighborhood around the point P, can I set the metric to Minkowski? So, of course, the metric is a smooth function of x prime. So I can write this as an expansion in x prime, a convergent Taylor series expansion in x prime. And I've only written the first two terms. The zeroth order term is eta mu nu because we are expanding around x prime equal to 0. And at the point x prime equal to 0, we have the metric to be eta mu nu, the Minkowski metric. Then the first order term, Taylor series, the first order correction, so on and so on and so forth. So the first correction would involve setting the slope parameter, the first order derivative, to 0. If we want d mu nu of x prime to be 0 for non-zero x prime, then at leading order, that is for small x's around this point, we must set this slope to 0. Okay, g prime of x should be such a function that the derivative of g prime with respect to the x prime at the point P, evaluated at the point P, should vanish. So how many equations are there? How many things we need to make vanish? Well, the derivatives g mu nu can take d times d plus 1 over 2, and the denominator can take d values because there are 3 derivatives. So we need to make satisfy these many conditions: d squared times d plus 1 over 2. All right, that would be equivalent to making these slope parameter vanish. So there's no correction to the Minkowski metric, and the first order the metric remains Minkowski around in a small neighborhood around x prime where you can ignore the higher order terms. So how can you do this? Well, remember the metric in general is determined by this kind of an equation, this kind of a transformation law. So the derivative of the metric will involve derivative of the Jacobian derivative of the Jacobian elements. So let me go back. So derivative of the Jacobian elements, which we need to doctor. The first order derivative has already been fixed because we wanted to make the metric at the point P eta mu nu. That took care of the slope parameters, slope variables we cannot touch anymore. They have been set. The only way we can change the rate of change of the metric is by looking at the second order derivative, the derivative of the Jacobian matrix element, and how many are there? Well, here, as you can see, the total number of parameter, numerator total number of components will be d because there's mu, and the denominator there is nu and rho. But remember, if I swap nu and rho, it doesn't make any difference because second order derivative, the order of the second order of the derivative doesn't matter. As a result, the denominator is symmetric in nu and rho. So the number of independent ways we can have symmetric combination of nu and rho would then be d times d plus 1 over 2. So the total numerator is d, and the denominator is d times d plus 1 over 2. The total number of parameters we get, which we can play with, is d squared times d plus 1 over 2, right? So this many conditions, which is exactly equal to the number of conditions. The number of parameters we can vary versus the number of conditions we need to satisfy are exactly the same. As a result, we can accomplish this goal, and we can make the metric Minkowski in a small neighborhood around x prime equal to 0 or x equals p, because the first correction to the metric vanishes. If we remain in an interval where the second order derivative, second order terms can be ignored, we can conclude in that small neighborhood around the origin, the metric is entirely Minkowski. Okay, this is what I've written. So at this point, the first order derivative also vanishes, and the metric is Minkowski. Provided higher order terms are negligible, we'll have this kind of situation. Now, this kind of a frame, this kind of a coordinate system in which the metric is Minkowski and the first order derivative vanishes is called a local inertial frame or geodesic coordinate, because the geodesic equation, if you remember the geodesic equation, let me go back to the geodesic equation. Here, the second term, which involves the Christoffel symbols, depend on the first order derivative of the metric, and we succeeded in setting the first order derivatives to the metric 0 by switching to the new coordinates. So the second term will drop out, and what we have in this coordinate system, where the metric is Minkowski and the first order derivative vanishes, is this equation. Now this is nothing but the equation of motion for a force-free motion. Okay, force-free motion. So geodesics become straight lines. If you integrate this, you'll be able to show that the geodesic is a straight line. Second order derivative with respect to the proper time vanishes. So in this frame, which is geodesic, as you know, a geodesic is the equation of motion for a point particle falling freely under gravity or moving under gravitational field. That appears to be that of a force-free motion. Okay, this is the force-free motion in inertial frames. So that is why a freely falling observer is considered to be an inertial observer in a gravitation. Now we can ask the question: can we make G mu, eta mu equal to eta mu in a larger neighborhood, even larger neighborhood? Okay, so that means the second order term in the metric should also vanish. The first order term we've already succeeded in vanishing by going to a freely falling frame, and you can ask whether the second term can also be made to vanish. So let's see if that can be accomplished. So the second order, that means the second order derivative of g prime with respect to the prime coordinates should also vanish, and the number of components is given by this. The numerator, because it's a symmetric in mu and nu, has this many independent ways you can this many independent combinations, and the denominator similarly is symmetric in an alpha and beta, has this many independent combinations. The total number of independent combinations and equal to the total number of independent conditions is square of d times d plus 1 over 2. Okay, so these many conditions we need to satisfy. Now let's see how many parameters we have at our disposal to play with, which we can use to set these conditions, to satisfy this condition. So let me go back. Again, the metric, second derivative of the metric would be second order derivative of the Jacobian. Okay, that would be third order derivative of the unprimed coordinate with respect to the prime coordinates. Okay, remember the first order derivative of the unprimed coordinate with respect to prime coordinates and the second order derivative of the unprimed coordinate with respect to the prime coordinates have already been fixed. There is no degree of freedom in left to touch those. The only thing we can use or we can play with is the third order derivative of the unprimed coordinate with respect to the prime coordinate. So, I'm sorry, there should be a 3 here. And how many are these? How many independent elements are there? Well, the numerator can take d values, and the denominator, because it's symmetric in all three, nu, rho, and sigma, it can take these many different values. So this product is given by this number. So this number we have at our disposal to play with to satisfy this many conditions. Immediately we see it's impossible to meet these conditions because the number of conditions or number of constraints is larger than the number of parameters we can play with. This difference is equal to difference of this minus this is equal to d squared times d minus 1 over 12. Okay, so evidently these number of second derivative of the metric will not remain 0, so we cannot set the second term and second order term in the Taylor expansion of the metric to be 0. Okay, so we cannot. So we can only make up to the first order 0. Now it turns out this number of components of the second derivative of g are exactly equal to the number of independent components of the Riemann tensor, which captures the tidal forces. Remember in your Newtonian gravity class, you learned that the tidal forces cannot be eliminated even if you go to a freely falling frame. And this is exactly the case. Even though we are in a freely falling frame, we can see these many components of the second, these many derivatives of the second derivatives of the metric cannot be set to 0. As a result, tidal forces cannot be eliminated, and this is exactly equal to the number of elements of the Riemann tensor, number of independent components of the Riemann tensor. All right. So I think we are done with today's lecture. Let me just summarize what we did today. First, we introduced the whirl line action of a massive spinless point particle. Although during the lecture I did not emphasize this, but I assumed that the point particle only has mass and no other physical attribute. But as you know from your other courses, that particle can have spins. For spinning particle, Geodesic equation is not the correct equation, and the action is not the correct action, which we wrote, the whirl line action. We need to add spin degrees of freedom or spin attributes of the point particle. That gives rise to a separate equation, which is called the Matheson-Petro-Dixon equation, which we will not learn in this course, but maybe in an advanced course in general relativity. For massive spinless point particle, we have the geodesic equation, which we learned today. We wrote down the geodesic equation in general, as well as affine parametrization, in which the right-hand side vanishes. And we also learned about a new quantity, which is called the Christoffel symbols. It's denoted by this weird curly brackets with mu in the upper index and nu in rho. I already mentioned that the Christoffel symbols are not components of a tensor. They do not transform like components of a tensor. Very easy to verify that because Christoffel symbols are made up of the inverse metric and the first derivative of the metric. So once you know the transformation law for the metric itself, it's very easy to deduce the transformation law for the Christoffel symbols. And if you do that, you will be able to see that they do not transform like components of a tensor. So we call them symbols. Okay, objects which have indices but do not transform like components of a tensor are called symbols. Now, Christoffel symbols, as I forgot to mention, are actually symmetric under swap of nu and rho. So if you swap nu and rho in the formula which I showed you before, you should be able to observe that it is symmetric. Physically, as I will explain later, Christoffel symbols represent the Newtonian forces, gravitational force. Then we learned about, in order to solve the geodesic equation, we learned about looking at symmetries of the metric, or isometries, as they're technically called. And they are given by the symmetries are generated by Killing vectors, which satisfy a Killing vector equation, which is that the Lie derivative of the metric with respect to the Killing vector must vanish. And these result in the existence of constants of motion, or conserved quantities, which reduces the equation of motion to first order, which we can readily integrate. And we also learned about local inertial frame. This is the frame in which geodesic equation appears like force-free motion, because the second derivative of x of the coordinate with respect to tau vanish. So this is a freely falling frame, as I explained, because geodesic is nothing but motion under gravity. So inertial frame, local inertial frame is same as the freely falling frame under gravity. Okay, so in this frame, the Christoffel symbols vanish and the metric is 0, of course around a small neighborhood, because tidal forces cannot be eliminated, and that's why it's a local inertial frame, locally around a small region around a point. One can have local inertial frames. All right, up next in the next lecture, we will learn about the important quantity called affine connection, denoted by gamma, and the associated notion of covariant derivative, covariant differentiation. We will learn about the torsion tensor. We will learn about the Levi-Civita connection, which is a special affine connection, which is torsion-free and metric compatible. This is what we will use in general relativity. Always we will use the Levi-Civita connection, which is torsion-free and metric compatible. And it will turn out that the Levi-Civita connection, when written in coordinate basis, coincides with the Christoffel symbol. Okay. At that note, I will stop. I'll See you next time. Thank you very much for your attention.